Okay, so today we're going to be actually evaluating our definite integrals using something called the fundamental theorem of calculus. So, this is one of the key things that will help us not have to spend all the time that we've been spending on our Riemann sums, and actually it opens up the doors to new functions that we can actually find the area between that function and the x-axis. Pretty much, we've got our standard stuff here with our fundamental theorem of calculus. We've got our integral from a to b of some function f of x with respect to x. And here, this is telling us is the antiderivative of f, of our little function, our little f of x. So big F is the antiderivative. What I can do then is evaluate the antiderivative at b and then subtract off what its value is at a, and that actually gives me what I'm looking for, the area between that function, the little f, and the x-axis. We'll often use the notation here at the bottom just to speed it up. So when we do our integral from a to b, we will actually end up saying that it equals our antiderivative, and then put this little bar from a to b, and it means the same thing. So we'll kind of step it out. We'll do step 1, step 2, step 3 each time we do this. So again, I abbreviated the fundamental theorem of calculus here and just put FTC. I'll probably start doing that more. So here we've got the integral from 0 to 2. Our function is 2x minus 3, and we're integrating with respect to x. So pretty much we have to find our antiderivative like we did before. I'm not going to maybe break everything down each time and expand things. I'm going to try to do some shortcuts here and there as I'm doing these. So we've got our 2x, and we're just going to do our power rule like we did before. So right now x is to the first power. So I've got 1 plus 1, which is 2. And then I've got to be over 2 because I had a 2 out front. So you can see that cancels out, and I'm just left with x squared. And then 3 has an x to the 0. So 1 plus 1 is, or 0 plus 1 is 1, and it's over 1. So my antiderivative is actually x squared minus 3x, and I'm going from 0 to 2. All right. And then all I have to do, I have to plug in my 2, and then I plug in my 0. So really, I'm equal to 2 squared minus 3 times 2 minus 0 squared minus 3 times 0. So hopefully you're sitting there thinking, wait, I know this last part's 0, so I really don't need that in this case. Sometimes when you have a 0 to 2, that's usually what's going to happen then. I don't want you to forget that step, so just do it every time. That way you won't mess it up. Over here we got 4 minus 6. So our final answer is negative 2. Again, it ends up being a lot less work than what we did before to find the areas. It just makes everything a lot easier. And it opens up new functions that here with this function, square root of x plus 3x, it would have been a lot harder to do Riemann sums because we didn't know how to do anything with that square root of x. So now we can actually do something with our antiderivative. Now, we're going to do like we did before, so we're going to change that to the 1/2 power so we can use the power rule. Alright, and as we go through after this, we'll actually find other rules and other ways of doing some of these antiderivatives like I was telling you before. So in this case, again, since I got that 1/2, I'll go ahead and write out the whole way the power rule works. So I've got x to the 1/2 plus 1 over 1/2 plus 1. And then the 3 has an x to the 1 plus 1, and it's going to be over 1 plus 1. And that's going to be evaluated from 0 to 4. Alright. So I got x to the 3/2 over 3/2. and then that's 3x squared over 2, and I'm going from 0 to 4. And again, hopefully I'm writing too many steps and you're like, okay, I get this. So we just really have to plug in our 4 here, but I'm going to go ahead and show you with the 0 as we're doing this. We got 2/3, and then I've got 4 to the 3 over 2 plus 3/2 of 4 squared. And then, again, we're taking away the 0 in this case, so I wrote minus 0. If we do this, we'll see that 4 to the 3/2 is 8. And we get 8 times 2, which is 16 over 3, plus 16 is 4 squared. 16 times 3 is 48. Divide that by 2, you get 24. And if I add those two together, you end up with 88 over 3. I know sometimes that's not the easiest thing to deal with the fractions, but you can verify this a few other ways. So the majority of our work on this section will actually just be using the first part of the fundamental theorem of calculus to evaluate this integral. So again, our antiderivative for secant x tangent x, if you look it up, hopefully remember that's secant x, and we're going from 0 to pi over 4. Okay, so that just means I need the secant of pi over 4 minus the secant of 0. Now, if you look it up on your unit circle, hopefully you remember secant's related to cosine. So let's start with the cosine of 0. Cosine of 0 is 1, so the secant of 0 is also 1, so I've got a minus 1 there. Secant of pi over 4. Cosine of pi over 4 is the square root of 2 over 2, so secant of that would be 2 over the square root of 2, and if you rationalize that, you end up with the square root of 2. And actually, in this case, since the square root of 2 is irrational, that's my answer. So the area between secant of x, tangent of x, and the x-axis between 0 and pi over 4 is exactly square root of 2 minus 1. So if you type in, there's a couple ways I'll show you. A couple people have already figured it out on Desmos, where you can actually type in this exact integral and it'll spit out a number, and it says 0.414, which is, and some change, which is the square root of 2 minus 1. And again, as we're looking at these right now, anything that you can do to make it simpler, simplify it down some. So in this case, I got e to the x over 2, and that whole thing is squared. So I can actually change that into just e to the x. So now I'm going from 0 to the natural log of 2. Wrote the wrong thing down up there. Alright, so if you remember, our antiderivative for e to the x is just e to the x. And we're evaluating from 0 to the natural log of 2. So I'm going to do e to the natural log of 2 minus e to the 0 power. If you remember our rules here, e to the natural log of a number is just that number. E to the 0 is 1, so my final answer here is 1. Okay, again, it's nothing too bad, but just take some time, take some practice, work on it some, ask questions if you don't understand what's going on. Right now, before we move on, somebody in my other classes requested that I do a little song and dance in the video, so I thought I'd show you what that might look like. So I hope you enjoy this pause from our regularly scheduled programming. Alright, I hope you enjoyed that. A little bit of fun there. That is actually what I dance like. So, that leads us to the second part of the fundamental theorem of calculus. Alright, so it says if f is continuous on a to b, and we know that our antiderivative, capital F of x, equals the integral from a to x of f of t with respect to t here now with our dt there. That means that our derivative of our antiderivative is just our original function with respect to x. Now notice this has a t in it, so if I'm integrating from a to x, then that's where this x is coming from. And you'll see some of them a little bit more challenging than others, but we'll get there. So here, find the derivative of f prime of x. Now one thing I noticed in the book around this problem number, I believe it's number 26, 27, the directions actually say a little f prime on mine. So that could be a typo because I'm pretty sure it's supposed to be a capital F prime. So check that out when you start working on the problems. Make sure you're finding the capital F prime, which is the antiderivative. So in this case, we've got something that looks a lot like what the fundamental theorem part 2 looks like. We're going from 0 to x, and then I've got t squared minus 3t plus 2 with respect to time here, the dt. I don't know why I said time, it's just with t. It's a dummy variable. So we're going from 0 to x, and guess what? By theorem 5.2, which is just what I showed you, we should know that since this is going from 0 to x, that the first derivative of the antiderivative is x squared minus 3x plus 2. It is that easy on this example. Some of them will work a little differently. I want you to work them out, see what you think of them, get the idea down, and then we'll go from there. Here's my last example. We are asked to find an equation for a tangent line at the given value of x. So, what you need to know here is that f prime of x is the slope of the tangent line. And we're going to use the fundamental theorem part 2 again to figure f prime of x out. So again, if we look up here, we're going from 0 to x. I've got a t squared in here. So that means f prime of x is going to equal the sine of the square root of x squared plus pi squared. Alright, that means the slope of the tangent line is going to, and I forgot my value of x here for some reason, it should be x equals 0. I didn't type that in for some reason. So we're going to figure that out when x is equal to 0. That will be the slope of our tangent line. So that should be a 0 there. So I've got 0 squared plus pi squared. And through some magic, the 0 goes away. And I'm left with the sine of the square root of pi squared, which is just the sine of pi, which equals 0. So, we got a 0 there. That's the slope of our tangent line. Now we got to figure out where the tangent line goes through, what other point. So our y-intercept. So we really, when we do that, we're going to go from this value to have x as 0 for this integral. And if I have matching values there, guess what happens? You're right, the integral is going to equal 0. So if the a and b match, that equals 0. So that means I'm going through 0 for my original function. My slope is 0. That means my tangent line is y equals 0. So again, tangent lines are always y equals mx plus b. And in this case, my m was 0, my b was 0. So that's the equation of my tangent line. Again, as you're working on these, just think about what can you do, what needs to happen, how does the fundamental theorem of calculus apply to help me find the value, and then we'll work on some of the other ones. If you get stuck, we'll work them out in class together. Just let me know.